Hello, everybody. Welcome to your lecture number 20 on physical geology. We're going to be studying rock deformation today and talking about the ways, basically, in which rocks can be deformed. Okay, so we're going to talk about all the different kinds of ways rocks can be deformed because we're getting ready to study earthquakes. Earthquakes result from rock deformation of different kinds. So anyway, you'll learn about a lot of exciting things today about folds and faults and stuff like that. That's kind of our goal for today. So hope you got your lecture assignment number 20 out. I know I have mine, and I got a nice binder for it now. So we're going to start here, lecture assignment number 20, and we're going to start by defining deformation. Okay, so let me move this on. I always have to turn on my pen. Here we go, pen. And oh, it's working this time, the first time. So what is deformation? Deformation is just any process that changes the shape, size, or area of the crust. Okay, so it's anything that's going to change the shape, size, area of the crust. Really, you could even simplify it even more. Just anything that's changing the shape of the crust. So, to change the shape of the crust and the crustal rocks, you're going to need some kind of force. And in geology, we call those forces stresses. Okay, usually they're tectonic stresses. Okay, those are the forces that are causing the deformation. Okay, so rocks don't just break. So I know that when you think of a rock deforming, you probably think of it crumbling apart, right? And you've seen me take this rock before and crumble it, and it breaks apart. And remember in the previous lectures, I broke it. And of course I made a big mess, but it breaks apart like that, and it makes a bunch of crumbs on my desk and stuff like that. So that's how you're used to rocks deforming, right? And that is a type of deformation. But there's other ways that rocks can deform too. They can actually bend, and that's called plastic deformation. So at a certain depth in the earth, rocks stop behaving like those brittle cookie type things, and they start behaving more like slime or something like that, right? Where the rocks can bend and fold and move and things like that. So that's another kind of deformation. We call that plastic deformation. So anyway, we're going to talk about all those different kinds. So rocks can bend, but they can also break, and they can also fold and do all sorts of things like that. So a lot of surprising things. So you maybe seen pictures like this before in your life, or maybe you've driven past a road cut and you've seen things like this where the rocks are bent and folded and contorted and tortured. Maybe you've seen something even like this. This is a really great picture because this is showing you that not only are the rocks folding like that, but they're also being faulted. So I hope that you can see, if you look at this, you can see like this bed right here. Okay, it abruptly stops. Okay, what has happened? Well, there's been a fault, and so rocks can be both faulted and folded. Okay, so I actually highlighted already the faults here in black, so you can see those. Okay, so there's another picture, just striking picture of rocks being both faulted and folded. Okay, so you can see that whenever there's a fault, you can see the fault lines right here. These are just little fault lines. Of course, they can be very big, but you can see that the direction of the fault's like this. Okay. And it's been offset. So you can see that this point used to be right there. So you can actually measure the offset, right? So that's called offset. Okay, so rocks can be, folds can actually be as big as mountains. So you can see folds here that are mountain-sized, right? Huge folds in the rocks. Obviously like miles and miles in size. And then folds can also be just very, very small. So these are like micro folds that you can find within a single rock sample. Okay, so a lot of different kinds of folds. This I wanted to show you. So stress is the force that causes the deformation. Okay, so he calls that stress. So all deformation in rocks is caused by a stress. So number 2, it says, what causes geologic deformation? It's very simple. It's a one-word answer. It's stress. Okay, stress is what causes the displacement. That means the moving of the rocks, like in a fault, the rotation or the strain. We're going to talk about strain in a minute. So stress causes deformation. So if you look at the folds you see in this rock, right, you can see all the folding of the rocks. What is that caused by? It's caused by this stress, okay? And usually stress comes in couples. Okay, what do I mean by couples? I mean in pairs. Okay, so a lot of times we call those stress couples or force couples. Okay, because it's like a squeezing of the rock, but it can also be an extensional kind of a coupling. So it could be pulling the rock apart as well. So force couples work usually in opposite directions, but they can also be offset from each other as well. And we'll talk about that later. All right, so here are the different kinds of deformation. So number 3, it says, what are the 3 kinds of deformation? You need to not only mention a word here, but describe a little bit. People, I notice, sometimes they forget to describe things. They lose some points on their lecture assignments. Okay, so make sure that you describe these as well. So the first kind of deformation that you can have is displacement. Displacement happens with faulting, happens with brittle deformation. And you can see, for example, look at this bed right here I'm drawing in the red pen. Okay, you can see that bed. All of a sudden it stops right here at a fault. Here's the fault. I'm drawing the trace of the fault right here. And it's continued. It looks like that bed continues right here. Okay. Like that. So that's what causes the displacement. So displacement means, or I'm saying the faulting causes the displacement. So displacement is when the rocks literally get moved. Okay, they just get moved. They get offset like that. All right. So one important word you need to know for this is offset. Offset. So a fault causes an offset. It means that a bed is interrupted. It breaks apart, and it's offset and displaced by a certain number, certain distance, whatever it's centimeters or meters or whatever. Another kind of deformation that can happen is a rotation. So rotation happens when there's a change in nothing is offset, but rocks are rotated. So this can happen where whole blocks of rocks are rotated like this. They didn't physically move per se, a certain distance, but they were rotated along an axis. Okay. The last thing that happens is called strain. Strain is when there's a change in the shape, and this is folding. Okay, so folds are a type of strain. Faults cause displacement. Folds are strain. Okay, strain is just a change in the shape of the rock, so it causes a fold. So displacement is associated with faulting. Strain is associated with folding. Okay, stress causes strain. Stress causes strain. So what is strain? It's just a change in the shape of a rock. That's number 4. Okay. So now we're going to talk about different kinds of stress. Here are some more examples of displacement. So you can see that this is a very famous picture actually from Hollister around San Francisco, from the 1906 San Francisco earthquake in Hollister, California. You could see literally the displacement caused by the earthquake in 1906. We'll talk a lot about that earthquake too. It's a very historically important earthquake, but you could see the displacement caused there. Okay, so displacement is a kind of deformation. It's caused by stress. It's caused by brittle deformation. Here's a good example of rotation. So I hope that you can see how these fault blocks have all been rotated. And I drew like a green bed here, just to kind of show you as kind of a marker bed, so you can see how the blocks have been tilted and rotated. Okay, so that's showing again rotation from stress. Okay, so you have the stress couples there. Actually, they're not showing stress couples, but it's showing stress arrows are causing the rotation of a bed. Okay. Last one is folding. That's changing the shape of the rocks. So strain. Right, we call that strain. That's when the rocks are folded and the shape changes. Okay, so a lot of times they get squeezed. They can also get pulled apart as well, though. All right, so these are the different kinds of 3 kinds of stress. So we're gonna draw this for number 5. I want you to draw the force couples that are associated with these different kinds of stress. Okay, now displacement, rotation, and strain are the things that stress causes. Stress can cause. They're types of deformation caused by stress. Okay? This is different now. Now we're talking about 3 different kinds of stress. So the first kind of stress is made easier to understand is called pure shear compression, aka compression. Okay? So here I want you to see that the arrows are coming together, the force couples are coming together, and they're directly opposed from one another. Okay? They're in line and they're directly opposed across from one another. That's pure shear compression. Okay? Directly opposed, directly in line. Then you can have the opposite. You can have pure shear extension, where something is being pulled apart. A rock is being pulled apart. Okay, that's pure shear extension. The other one is a little bit different. This is where the stress couples are offset. Do you see that? That is called simple shear. Now they are offset. Okay, so those are the 3 different kinds of stress that can cause strain. Very important to keep your vocab straightened out here, because I know it's really, I think a lot of people just think of stress as the same as strain, and in geology we use they mean different things. So stress causes a strain. Okay, so there's tensional stress, right? That's pure shear extension. Compressional stress, that's pure shear compression. And shear stress, notice how shear stress can shear the rock, cut the rock into 2. Okay, so again, here's pure shear compression. Okay, that causes a collision and mountain building usually. We have pure shear extension. That causes the Horst and Graben, or the basin and range kind of. Remember I talked about basin and range a little bit in the last lecture. That causes the basin and range kind of topology. See, with the mountains and basins and mountains and basins, mountains and basins, etc. And then we have simple shear. That's like a transform boundary. Okay, remember we talked about the different kinds of boundaries. Notice how the different kinds of stress correspond to different kinds of plate tectonic boundaries. So this would be, convergent. This would be divergent. And this would be transform. Okay. So now let's talk about another thing. We got down to number 5. We're going to do number 6 now. We're going to talk about brittle deformation versus ductile deformation. This is pretty easy to understand, I think. Brittle deformation, look at this picture. I have all this china and all this plates and saucers and things, bowls that are broken. Okay, that's brittle deformation. So remember, I broke this rock, right? I broke it into crumbs, and it crumbled everywhere. And that's the kind of, maybe what you would think of as the natural way of understanding how a rock would respond to a stress. You squeeze it, you twist it, you put a force on it, and it breaks and crumbles apart. Okay, that's brittle deformation. Brittle, kind of like breaks like a cookie. Ductile deformation is more like the cookie dough. Okay, with ductile deformation, the rocks are able to bend and fold and able to strain. So now you have a strain. So strain, remember, is changing the shape. With brittle deformation, you don't really change the shape of the saucer, right? You could take the saucer, and after it breaks, you can glue it all back together, and it's the same shape. With ductile deformation, you have changed the shape. So you've warped the shape of the material. So, if you, again, I think the best analogy is thinking of a baked cookie. That's brittle deformation. Versus cookie dough. That's like ductile deformation. So, with a cookie dough, you can squeeze and change the shape of the cookie, make it round or square or whatever you want. Okay. All right. Now, what determines, this is an important thing, what determines if a rock is going to break brittly or if it's going to fold and behave and deform ductily? So what's going to determine whether or not we're going to have brittle deformation or ductile deformation? Okay, so it's responding to a stress. What's going to determine whether it behaves brittle or ductile? Let's talk about that. So all 4 of these things, play a role. temperature. At high temperature, you can probably guess that if something gets warm, the rocks get warm, they get, or I shouldn't say warm, but hot, really hot, kind of like melted butter, they're going to start to be able to fold and bend and deform ductily. Whereas you probably have an intuition that cold things are going to be more likely to break brittly. Okay, so increase in temperature makes rocks more ductile. Okay, pressure is the next thing. At high pressures, rocks also tend to deform ductily. So it's harder to break materials under high pressure. So it's actually easier for the atomic bonds to be stretched rather than break at high pressure. So that causes the ductile deformation. Rate. Strain rate makes a big difference here. When you deform something quickly, you apply the stress very quickly, it will often break brittly. So think of a hammer coming down and smashing a rock. That's a very fast application of the stress. The stress comes in a matter of microseconds and it's over. However, think about if we very, very, very slowly pull the rock apart. That's a different kind of strain rate, and that's going to cause the material to behave more ductily. We can actually do the same thing with slime. See, I'm always using my slime as a metaphor. So if I take this, I'm going to make it big. So if I take this slime, if I make a strain rate that's very fast, so I'm just going to pull this apart real fast. Notice I broke it. I broke it into two pieces. That's a fast strain rate. Okay. However, I can let the strain rate, just let this fall naturally, and instead of breaking, it stretches. Rocks do the same thing. So if you apply the stress very slowly and gradually, instead of just snapping it off, it will behave and break. It'll behave ductily rather than brittly. Okay. So strain rate plays a role as well in determining, get this stuff off my hands now. Strain rate plays a big role in whether a rock will break brittly or deform ductily. And then the final thing is composition. Some rocks are just a lot better at breaking. Whoops, here we go. Where are we? Oh, my draw tool turned off. Some kinds of rocks, like different compositions of rocks, are just a lot better at behaving ductily versus brittly. For example, halite, like rock salt, is very, very ductile. It's very easy for it to behave ductily. Whereas other rocks, are like granite, for instance, are much more inclined to break brittly. Okay, so let's talk. We talked about number 6. What's the difference between brittle and ductile deformation? Let's talk about number 7. What depth does ductile deformation typically occur? So you know that here at the surface, where the temperatures are cold and the pressures are low, that rocks are going to break brittly. They're not going to fold, right? I don't think that any of you have ever been around a rock that you can actually take in your hands and fold it instead of just, break it. So you're going to guess that at the surface, brittle deformation is much more common. And in fact, that is true. So this is a good diagram that shows you depth and what kind of rocks you get, what kind of deformation you get as a function of depth. Depth. This over here is the strength of the rock. So I told you that some rocks are less strong, right? So they're weaker. They're more inclined to ductile deformation. So for example, halite, rock salt, limestone, marble, things like that are more inclined to ductile deformation versus things like granite or Granite is like it's much stronger, so it's a stronger rock. So this is showing the strength of the rock on the y-axis. Now, if you go over here, you see that you don't really get any kind of brittle deformation, you don't really get any ductile deformation until about 15 kilometers. So you have to get down to 15, all the way down to 20 before ductile deformation really takes over. By the way, whenever you see this word plastic, crystal plastic processes, plastic means moldable. That's what plastic means. The reason that we call stuff like, your pen that's made of plastic, the reason we call that material plastic is just because it's a moldable material. That's really what it is. It really a proper name for this is a polymer. It's a plastic polymer, and it just got shortened. That word plastic polymer just got shortened to plastic. But plastic really means moldable. You can make a mold out of it. Okay. So anyway, I forgot to turn the screen back on. You're not even seeing what I'm drawing. Go like that. Okay, now you should be able to see it. So I was just showing you on this thing the brittle ductile. Whoops, gosh, I forgot to turn the pen on again. Here, pen. There we go. The brittle ductile transition zone doesn't happen until about 15 kilometers. Okay, so at 15 kilometers. Whoops, there we go. At 15 kilometers, you'll start to transition over from brittle deformation to plastic deformation, okay? Ductile deformation. All right, so typically for the continental crust, rocks deform by brittle deformation shallower than 15 kilometers, and then once you get deeper than 15 kilometers, you get ductile deformation, okay? But again, deformation rate, the strain rate, is an important factor, okay? So it can depend on those other factors like temperature and the deformation rate, the strain rate, and the composition of the rock. Okay. All right. So let's talk about different kinds of brittle deformation. So we also have different kinds of brittle deformation. Let me get this here. Okay. So this is we're going to get to strike and dip in a minute for number 8. We do have to talk different kinds of faults and stuff like that. So brittle deformation is mostly faulting, although you can get things like joints. Joints are natural cracks that develop in rocks in a response to tensile stress. That means tensile means pull apart stress, extensional stress. So tension, okay? Tensile, tension, extension means pulling apart. Okay, so this is a good example, a good picture of vertical jointing that's happening from temperature cracking. It's from cooling. So it's the same kind of thing that happens in your windshield. If you ever were to pour hot water on your windshield, like boiling water on your windshield on a cold day, a lot of people do that thinking they can melt the frost off their windshield, and their windshield cracks, right? Why does it crack? It cracks from extensional stresses because you're rapidly changing the the thermal expansion. Okay, so you're rapidly changing the temperature. You're causing thermal expansion in the glass, and it shatters the glass. Okay, and again, strain rate plays a big role there because you're rapidly changing the temperature of the glass. If you were to slowly change the temperature of the glass, there's no problem, right? But it's rapid changing that causes it to break. Same thing can happen with rapid cooling in a magma. It can create all these tensional cracks. So you can see all the cracks that are happening vertically here. Same thing happens from pressure cracking. Remember we talked about all this stuff when we talked about weathering, right? These are all types of brittle deformation that happen in rocks. So this is not faulting. We're going to talk about faulting right now. But I just want you to be aware about joints and cracks like that. Okay. Now let's talk about faulting. There are 3 kinds of faults that's asked about in number 9. Okay, you have 3 kinds of faults we're going to talk about here. So the first kind of faulting is called normal faulting. And normal faulting happens, I'm trying to draw on here. Okay, so you can see the fault line here. I'm trying to draw the fault line. And you could see that one side of this, my arrows are all kind of messed up. I don't know what happened to my arrows. Oh gosh. Whoops. My arrows are all messed up there. Where'd it go? Where'd it go? Oh, right here. Okay. I'm just trying to change the arrows. There we go, like that. I must have moved the picture. Okay, so you can see with normal faulting, whoops. One side of the fault block is going down, the other side's going up. Now I want you to take a look. Here's the fault plane. And this fault block is moving down the fault plane. So you see how there's a kind of a tilt to the fault plane, almost like it's going downhill and uphill? This fault block is moving downhill. It's moving down the fault plane, sliding down the fault plane. That results from tensile stresses, pulling apart stresses, okay? Whereas this one is moving up, okay? So that's called a normal fault. A strike slip fault results from simple shear, right? Remember when we have an offset in the force couples, and you get a shearing, so you get this side by side motion. Okay, so there's strike slip faulting right there, and then we can also get reverse faults. So reverse faults is the opposite of a normal fault. In fact, and what will happen is one of these blocks will move up along the fault plane instead of down. Okay, so I'll show you more pictures of that in a minute. But you should know that there's reverse, which happens with compressional stresses. There's normal, which happens with tensile stresses, extensional stresses. And there's strike slip, which occur with simple shear, the side-by-side offset force couples. Okay. All right, now I want to talk a little bit about strike and dip. Very, very hard concept to understand, especially when we're online like this, and I have to try to show you via pictures. But there are a lot of deformation. We encounter all sorts of different kinds of deformation in nature, and we want to try as geologists to record and observe the deformation we see, and we want to try to come up with a universal way that we can communicate the orientation of different features, like fault planes, bedding planes, and things like that. Strike and dip is the way that geologists express the orientation of planar geologic features. I'm going to say that one more time. Strike and dip is the way that geologists express the orientation of different planar geologic features. Planar means shaped like a plane. What is a plane? A plane is a flat surface, okay? And flat doesn't mean horizontal. That's a flat horizontal surface. This is a flat surface, right? There's a planar shape. It's a plane. That's a horizontal. That's a vertical planar feature. That's a horizontal planar feature. But we want to be able to express as geologists what is the orientation of this plane. Okay. So I want you, maybe I'll make this big so I can okay, so now it's bigger so you can see this. I just want you to see this. So this is my flat plane. And I want to be able to express what is the orientation of this plane. Now maybe this plane, this is my plane right here. It's just my binder. Maybe it is a dike. Maybe it's a fault plane. Maybe it's a bedding plane. Maybe it's a sill. There are so many different, or maybe it's a plane of joints, right? There's so many different kinds of planar features in geology, and we want to be able to express those different kinds of planar features. So we can have a horizontal plane like that, right? It's horizontal. We could have a vertical plane, and we can have everything in between, okay? So we need first of all, we need a way of expressing how it's dipping, okay? So this is flat, this is vertical, and there's everything in between. So the way that we express that dip, we have that term dip, and expresses how it's the angle in relation to horizontal. Okay, so that's horizontal, that's vertical, and then we have a dip that expresses the angle relative to horizontal. Okay, I'll get more into that later. Now, not only did that, but see, there's a difference. Let's say we have the same dip. So here's my dip. But this could be rotated like this or rotated like this. It could be dipping to the north. It could be dipping to the south. It could be dipping to the east or to the west or whatever. So we need a way of expressing which direction it is dipping towards. Okay? So what we use is something called strike and dip. So strike and dip goes like this. First of all, we have the dip of the feature below a horizontal plane. Okay, so let's say we have a roof. I think a roof like this one, right here. Got to turn on my pen again. This roof right here. This is a pretty good way of imagining strike and dip. So think of this side of the roof right here. Okay, it's dipping below horizontal. Okay, and it's dipping how much? Well, it's dipping about 45 degrees from the horizontal. So it's moved 45 degrees down off of horizontal. Okay, but that's not enough to explain and express the total orientation of that roof. It's not enough to just say how much it's dipping below horizontal. We also have to say if it's dipping towards the east or the west or the north or the south. So we do that using strike. Strike is the angle from north of the intersection between the exposed plane and surface, a perfect horizontal surface. So it is the intersection between the dipping plane and perfect horizontal surface. Okay? So you'll notice that the strike of this roof, this line right here I'm drawing, do you see that? Let me use a different color so you can see it. I'm going to use blue. This line right here, where the roof intersects with a perfect horizontal, and I mean it's the same, I could draw the same line right here, right? It's the same thing. But it's intersecting with a perfect horizontal surface. You'll notice that it makes a trace along the surface like that. That is the strike direction. So in this case, the strike direction is east-west. But then we have to ask a question, because remember, it's the angle from the north. That means going clockwise from north. Is how we express the strike. So in this case, we start at north, and we start going, and we see that we get to the east. So the strike of this roof is 90 degrees. Okay, it's east, and the dip is 45 degrees, and it's dipping to the south. Okay, so that's how we express the orientation of a plane in geology. Again, if you look at this rock, okay, this rock is striking east-west because you can see that the intersection of the bedding plane, the intersection that it makes with a perfectly horizontal surface, is going from east to west. Okay, so we put the strike direction as east, and the dip angle is 45 degrees. Okay, so these planes are tilting 45 degrees away from a perfectly horizontal flat surface, and it's dipping to the south. The dip direction is to the south. Okay. We use the right hand rule in this, by the way. So you put your thumb along the strike, and your finger will point in the dip direction. Okay. So again, here's an example of something that is not exactly the strike is not exactly along the cardinal directions, right? East, west, north, south. So here, this direction is north. Okay, you can see this direction is north, and you can see that the strike of this bedding is not directly north. In fact, it's right between perfect north and perfectly east. So it's actually about 45 degrees. Okay, so the 45 degrees. Just a little thing here. I have to explain about azimuth. So imagine a compass. So I'm going to draw a compass right here. Actually, maybe I already have do I have a picture of this? No, I don't have a picture. So let me draw this. Actually, hold on. Let me just pull up a picture. I should get a picture off the internet. I really should have gotten this. Okay. So we go here. Let me look up. I want something like this is pretty good. Maybe this one. Okay, let's copy that and put that in here. So yeah, that's good. Let me show you this. All right, so again, I should kind of put this in before. When we're expressing strike, we want to give an exact compass direction. Okay, it's not enough. We want to, in science, we want to be very exact. So we don't want to just say north, south, east, west, or like north, northeast, or south, whatever. We want to be more precise than that. So we're actually going to apply a number to it, not just a direction like southwest or northwest or whatever. Okay, we're going to apply a number. So the first number, perfect north is 360 degrees or 0 degrees. Okay, it's the same. And then perfectly east is 90 degrees. Okay, and you see that it makes a 90-degree angle with north. South is 180 degrees. West is 270 degrees. Okay, and then we have all the other degrees in between. Okay, so we have all the other degrees in between. And we use 10, 20, 30, 40, whatever it is. Okay, so that's called azimuth. So with strike, we're always going to use azimuth. All right. So the strike, you'll express the strike as an azimuth, which is a number, right, between 0 and 360 degrees. Okay, or I guess 359 degrees, whatever. But anyway, that's how we're going to express the strike. Okay. So the strike here is 45 degrees. Okay, this is 45. And why is it 45? It's because it's 45 degrees from north. So you can see that it's going in this 45 degree. Maybe I could even copy this. Whoops. There we go. Maybe I could even superimpose this. You can kind of see what I mean. Whoops, like this. No, it doesn't work. Like that. Nah, I guess that looks too confusing. But it's all right. I hope you get the idea. I'm sorry. This is hard stuff to explain. It's hard. It's hard enough in person when I have people sitting there right down with me and I can show them this on a compass, but it's even harder over the internet. So I hope you're getting it. But anyway, I want to look at number. Let's look at what number you're doing here in the lecture assignment packet. So doing number 8. Now number 8, it's pretty easy, I think. But hopefully you can understand what the strike and the dip is of that inclined plane that's shown on number 8. Okay. All right, so again, one more thing just to kind of practice. We're looking east here. Okay, so we're looking east, so this is 90 degrees. Over here would be, this direction would be north. Whoops. Would be north. So that would be 0 degrees. This way would be south, that'd be 180. Okay, south. So we're looking to the east. Now we see do you see this bedding plane, right? And you can see the strike because the bedding plane is coming right up out of the water, which is a perfectly horizontal flat surface. So you can see that the strike is going directly to the east. Okay, now does that mean the strike is east? I'm not exactly sure. We have to use the right hand rule. So you put your thumb, you kind of have to put your thumb along, imagine you putting your thumb along the strike, and you have to point, your finger has to point, so I'm kind of orienting myself to what I'm seeing. Your finger has to point down the dip. In this case, we are striking 90 degrees, okay? So our thumb would be pointing 90 degrees east, and our finger, our pointer finger of our right hand would be pointing down the dip. So that's how we know that it's striking 90 degrees. Because somebody could look at the same thing and say, well, is it striking 90 degrees or is it striking 270 degrees, which is west? We figure out if it's west or east, 90 degrees or 270 degrees using right hand rule. Your thumb points in the direction of the strike. Your finger points down dip. Okay, then the dip direction. So this is what is the strike of the bedding? It is 90 degrees. What's the dip direction of the bedding? It's to the south, right? See how it's dipping to the south? What is the dip angle of the bedding? I have no clue because I don't see. You would have to measure it with like a protractor or something like that. But it looks to be maybe like, I don't know, 20 degrees, something like that. Okay, it's dipping below horizontal. Now let's look again. These are all dipping. We're looking to the south. What's the strike of the bedding? So the strike seems to be going north-south. Okay, seems to be pointing in the south direction. Now, which way is it? So I'm going to use the right-hand rule, and it looks like the strike is going to be, if I put my thumb along the strike, it'd be pointing to the south, and the dip direction, my finger would be pointing, and my right hand would be pointing to the, what direction would it be? I guess it would be to the west, right? So I'm looking to the south, and if you're looking south, yeah, your right hand would be to the west. Okay, so it's the strike is to the south. The dip, I can't tell what the dip direction is to the west. The dip angle looks like almost vertical, not quite vertical, but almost vertical, maybe 80 degrees or something like that. So it's a high angle dip. So anyway, I hope that all makes sense to you. I know it's complicated, but I tried to do a bunch of examples there for you to explain strike and dip. On the test, expect a question kind of like number 8. You would have a block diagram like that. I would have to give you the dip angle because you wouldn't have a protractor to measure it, but I would give you a strike that goes along one of the cardinal directions, north, south, east, west, something like that. Okay, so let's go on to faults. Again, I kind of introduced this a little bit to you earlier. So we have 3 kinds of faults I want to talk about. Reverse faults, normal faults. By the way, I shouldn't have put this here. This is a thrust fault. Thrust fault is just a low angle reverse fault. But I want to express something here to you. So with fault blocks, okay, with these fault blocks, you see that there's a fault plane. This is the fault plane. These are the fault blocks, okay? Fault blocks. Okay, with the fault blocks, imagine that you were walking along a fault plane. So imagine you were a miner underground, you're walking along the fault plane underground. And let's say, because a lot of times they would dig mines along faults because they were easier to mine, and also a lot of ore minerals would get deposited along the cracks around the faults, okay? So historically, a lot of miners would be mining around faults, and they would be walking along the fault plane and digging along the fault plane. So your feet, notice how your feet are touching the bottom of the fault plane. We call that block the footwall. And we call the one on top where you would hang your lantern if you were a miner, we call that the hanging wall. So when the hanging wall moves up in relativity to the footwall, it's sliding up the fault plane. The hanging wall is sliding up the fault plane. We call that a reverse fault if it's high angle, a thrust fault if it's low angle. If it's sliding down, the hanging wall is sliding down the fault plane, we call that a normal fault. If the fault blocks are moving side by side, we call that a strike slip fault. And it's either going to be a right lateral or left lateral strike slip fault. Now you might ask, how do you know if it's left lateral or right lateral? If you look at the fault and you see everything across the fault is moving to the right, it's a right lateral. If you're looking at the fault and everything on the other side of the fault is moving to the left, we call it a left lateral strike slip. All right, so here's an example of an exam question. Okay, so this is the 2011 Japanese earthquake. Is it a left lateral strike slip fault or right lateral strike slip fault? So hopefully, obviously, it's not a strike slip fault at all. Okay, because those are moving side by side. What's happening is you have a low angle, and you can see that the hanging wall is moving up the fault plane, right? So it's either, you could either call this a thrust fault would be the most correct, or a reverse fault. Okay, a reverse fault is the hanging wall moves up the footwall, Thrust fault, the hanging wall moves up the footwall, but a thrust fault is low angle, a reverse fault is high angle. So you see how there's an angle. Let me erase the stuff on here. You see how there's an angle difference in the orientation of the fault plane here and here. That's a low angle LA, low angle. This is a high angle HA. Okay. Now take a look at this. These are the strike slip faults. See, if you're standing over here, or let's say, and you're looking at that man's going to appear to move to the left, right? That means it's a left lateral strike slip fault. If you're standing over here and you're looking at this man, he's going to move to the right after the earthquake, and that's going to be a right lateral strike slip fault. Okay. So looking at the San Andreas fault, here's the stream bed here. Here's the other stream bed. This is the offset, right? Here's the offset right here. So you notice that this stream bed on the other side of the San Andreas fault moved to the right. That means it's a right lateral strike slip fault. Okay. So it's B. All right, so you got strike slip. Sometimes you have things like dip slip and oblique slip. I don't think I'll test on that, but just kind of be aware that those kind of things exist. But they're a mix. You can have things that are a mix of strike slip and normal or reverse faults. So they're kind of a mix. A lot of faults in real life are not just pure strike slip or pure normal or pure reverse. There's some mixture of strike slip along with normal. So we give different terms like dip slip or oblique slip to things like that. Okay, so for number 10, you should be able to classify those faults based on the block diagrams. For number 11, is the strike slip fault above left lateral or right lateral? You got to figure that out. In the block diagram, label the hanging wall and the footwall. Okay, and how would you classify a fault in which the hanging wall slipped down? The footwall. Okay, we talked about that already. Last thing we need to talk about are different kinds of folds. This is pretty simple. By the way, one thing I want to talk about too, final thing with faults. With faults, how do you recognize a fault in the field? You look for a marker bed. So, a lot of beds will just stick out. They're very prominent. So, like, for example, this bed right here is very prominent. It's the same as this bed. So you can see that there must be a fault right here. Because remember way back Steno's rule of lateral continuity, right? Beds don't just start and end abruptly. They go on almost to infinity. Not really, but they go on for miles and miles and miles. So you're not just, when you see a bed like this just abruptly end, see how it just abruptly ends right there? That's a fault. Whenever you see a very prominent marker bed just end abruptly, there's a fault there. So you could see that the fault was moving like this. This is up, this is down. So this is the hanging wall moving up the fault plane. So this is a thrust fault, which you see right there. Okay. So sometimes you see things like fault scarps, fault breccia, lineations. So you can actually see these like scrapes that happen called lineations along the fault scarp. Fault scarps are the kind of scars that are left on the landscape after there's been a fault and or an earthquake, and and you can actually see and stand on top of the fault plane. They're pretty cool. Okay, so let's get on to folding. So folding, rocks bend, and we give different names to the different structures. The main things I want you to know are anticlines and synclines. So anticlines are when the fold is an upright fold, is going up and making kind of a dome shape. A syncline is when you get a bowl, the opposite of a dome, you get a bowl shape. So when you have a dome-shaped fold, you call that an anticline. When you get the opposite, and it's like a bowl-shaped fold going down, we call that a syncline. So there's the anticline, there's the syncline. Okay, so what do you think of that? Is that anticline or syncline? So hopefully you can see the folds and the rocks, that is a syncline. Okay. Some things I want to see. So you have to label the hinge and two limbs and the axial plane. So here's a little bit more into how we the anatomy of a fold. So you can see the apex of the fold, where it turns and transitions going in the other direction. We call that the hinge, and we can draw an axial plane that goes along the hinge line. Okay, so it's the hinge of where the two limbs are folding. So these are the different limbs of the fold, and they come together. The different limbs of the fold come together and turn at the hinge line. Okay, just like the hinge in a door or a cupboard or whatever. Okay, so hopefully again you can see the limbs coming in here of this anticline, and it's going down right here. So there's like a hinge line right here. Okay, so this is a limb, this is a limb here, and you can see the hinge line is like right here, and that's the axial plane going into the, I tried to draw the axial plane right here. It's kind of hard with what I have in PowerPoint, but imagine these things three-dimensionally, but that's how that all works. So there again, by the way, sometimes you can have hinges that are sideways. They don't have to be perfectly upright, so you can see that this hinge line is kind of tilted off kilter, right? So there you go. Sometimes folds can plunge into the earth, and you can actually see the fold in the aerially above, right? You don't have to see it necessarily horizontally at a road cut. You can see it superimposed down into the rocks. Okay, things like monoclines you don't necessarily need to know, but anyway, I think I covered everything. So let's talk about possible exam questions you could have. All right, so stress is the amount of force applied per unit area of a surface rock. It is just the force that is changing the shape of the rock, or it's causing deformation, I should say more precisely. Strain is a type of deformation. It's caused by a stress, and it changes the shape of the rock. Okay? 3 different kinds of stresses, right? We have pure shear compression, pure shear extension, simple shear where the force couples are offset. Remember that strain, there's 2 kinds of strain, or I shouldn't say there's 2 kinds of strain, but we get brittle deformation, ductile deformation. Remember that strain changes the shape, so really strain is a type of ductile deformation. Whether something deforms ductily or brittly is going to depend on temperature, pressure, the strain rate, and composition. We talked about strike and dip. Just make sure that with a simple diagram like you have for number 8 in your lecture assignment, just know that make sure that you can label that and say what the strike is, what the dip is. Okay. About folds, make sure that you can identify an anticline and a syncline, and make sure that you can draw in there the limbs, the axial plane, and the hinge line. Okay. So here are some specific exam questions. How is stress different from strain? So remember that stress causes strain. Okay, so stress is the change in the shape. Strain is the change in the shape due to here we go. Strain is the change in the shape of a rock due to applied stress. Okay, that's a good way of putting it. C. The fold in the picture on the right is a anticline. Okay, it's an anticline. Regularly spaced joints in an outcrop may indicate that an area is under intense shear stress, has experienced compressional stress, underlain by a normal thrust, or underlain by a thrust fault, or is formed from a rock that were at once at great depths. So we know that this is not true, because rocks that were at great depths are going to be more inclined to ductily deform. Thrust faults don't have anything to do with it. Remember that joints are more about, remember we get joints when we get things like extensional or compressional. So shear stress isn't going to cause joints, so it's probably going to be experienced compressional stress. Okay, so B. And that's all I have for you today. So anyway, hope you enjoyed the lecture. We're going to continue next time with earthquakes 1 and 2, and we'll have volcanoes 1 and 2, and then we'll have one final lecture on Earth history and the kind of history of life on Earth, geologic time and all that. And then we'll be all done with the class. And then you can go on to new and better things. So anyway, I hope that you enjoyed the lecture, and I'll talk to you next time.